Welcome back to The Explainer. Okay, today we're diving into what is literally a biomedical detective story. How do our organs secretly communicate? How do they age? And maybe most importantly, how do they miraculously rejuvenate? We're going to decode the microscopic highways of systemic transport, essentially summarizing the core dynamics of organ rejuvenation and uncover some absolutely incredible secrets of human biology. We've got a clear roadmap for The Explainer today, so you know exactly how we're going to unpack this whole mystery. 1. Anatomy of systemic transport. 2. The macroscopic transport loop. 3. The concentration paradox. 4. Rejuvenation, looking at the brakes versus the gas. And finally, number 5, future therapeutic frontiers.
Okay, let's dive into this. What you're seeing here isn't just static biology. It's a bustling, microscopic highway system. These pathways dictate everything from how nutrients actually reach your cells to how cellular waste gets completely cleared away. And understanding the physical barriers within these interstitial spaces, well, that's absolutely crucial. It's the key to unlocking the secrets of cellular aging and tissue repair.
Now, consider this the blueprint for our entire investigation. Think of it like our crime scene map. Over on the left, you've got the anatomical infrastructure, the actual physical pipes and filters of the body. Right in the middle is the massive concentration paradox that cellular signals somehow have to survive. And on the right, the clinical holy grail itself, organ rejuvenation. Keep this blueprint in mind, because everything we unpack today builds directly on this exact foundation. Section 1, Anatomy of Systemic Transport, the physical infrastructure. All right, look at the left side here. You've got these continuous capillary structures, the kind you'd find in places like your muscles or your brain. They're highly guarded. They actually require active, energy-dependent transport, like penocytosis, just for molecules to cross. But check out the right side. Those are fenestrated capillaries, found in organs like the liver, the spleen, and the kidneys. These things are highly porous. They allow for passive, gradient-driven diffusion right through physical gaps. So it's literally a completely different rulebook depending on exactly where you are in the body. Now, zooming into the kidneys, we find a highly specific gateway. Pay attention to those exact dimensions, 80 to 100 nanometers. While general tissue fenestrations might be, say, 60 to 70 nanometers, this specific renal dimension acts like a strict microscopic bouncer. It dictates exactly which plasma proteins and targeted exosomes are allowed to transition from the bloodstream straight into the local renal tissue. And this brilliantly illustrates what happens next. Because once molecules leak into the tissue space, they don't just sit there in a puddle. No, the lymphatic network operates as an omnipresent vacuum engine. By utilizing negative pressure and some clever mechanical backflow prevention, it continuously vacuums up any unutilized signaling molecules, cellular waste, and excess fluid, physically driving them away from that dense local tissue environment. Section 2, the macroscopic transport loop, mapping the flow. So, your local tissue environments are permanently linked to your systemic circulation in this continuous pressure-driven fluid cycle. It's an amazing piece of plumbing. Anything that gets picked up by that lymphatic vacuum engine eventually merges into larger trunks and always, without fail, terminates right back at the right atrium of the heart, seamlessly re-entering the bloodstream. Just quickly following the flow here, your signals travel through the systemic blood circulation, they escape via gateways like the glomerular filter, they enter the dense interstitial space of the tissue, they get cleared out by the lymphatic vessel vacuum, and finally, they return right back to the right atrium to start the whole shebang all over again. It is a brilliant, entirely closed-loop machine. Section 3, the concentration paradox, the biological roadblock. I want you to really lean in and think about this crucial question for a second. If one single cell secretes a signal in tiny microscopic amounts, literally picograms or nanograms, how on earth does that tiny signal survive massive systemic dilution across liters and liters of blood to actually affect a change in a completely different distant organ? By all standard logic, standard soluble factors should mathematically be completely lost. Now, what's really interesting about this slide is seeing exactly where that biological roadblock hits. Look at the local secretion on the left. It's super concentrated right next to the cell. But the absolute second it enters that massive systemic circulation volume on the right, it completely scatters. The physical laws of osmolarity and dilution render traditional soluble protein signaling incredibly inefficient at a systemic scale. To completely grasp this, let's just do a quick refresher on two concepts. Paracrine signaling is local. It's cell-to-cell communication relying on highly effective, localized concentration gradients. Endocrine signaling, on the other hand, is long distance. Endocrine signals have to brave the vast fluid volume of the entire circulatory system, facing that massive, immediate systemic dilution we just talked about. Comparing these directly really puts it into perspective. On the left, local paracrine impact is highly effective. That concentration gradient is strictly maintained, ensuring the receptors right next door actually get activated. But on the right, the systemic endocrine signal is completely lost in the noise. Standard soluble actors like FGF or VEGF rely entirely on concentration gradients. Without a high local gradient, they literally physically fail to trigger responses in distant cells. So how does the body engineer around this seemingly impossible barrier? Well, it uses two brilliant workarounds. The first leverages constant hyperfiltration in the kidneys. Even if molecules are highly diluted, forcing massive volumes of blood through that filter naturally hyperconcentrates those signals locally over time. The second workaround, it uses enveloped factors, targeted exosomes. Think of exosomes as protective armored delivery trucks that completely ignore concentration gradients to survive the bloodstream and dock structurally with specific affinity receptors. It's a real game changer.
Section 4. Rejuvenation phenomenon and breaks versus gas.
All right, enter the mind-blowing world of heterochronic parabiosis. This is a fascinating phenomenon where you connect an older, aging circulatory system to a young, healthy, systemic circulation. And the result? The older system actually exhibits measurable tissue repair. The ultimate question we're trying to solve here is, how does this happen, especially given all those microscopic transport barriers we literally just explored? Let's ground this in some observable medical reality. Clinical transplant data shows us that when an older donor kidney, say from a 60-year-old, is transplanted into a much younger recipient, the older organ doesn't just merely survive, it exhibits predictable, measurable improvement in physiological function. The young systemic environment actually rejuvenates the old organ. It's absolutely incredible. So, the crucial point is figuring out the how. We've got the breaks versus the gas hypothesis. Does the young circulation simply dilute and clear out the suppressive aging toxins that are pooled in the old interstitial space, basically taking the foot off the biological brakes so the organ can self-repair? Or is it the gas? Does the young blood actively deliver exogenous stem cell factors and targeted exosomes to actively force regeneration? The reality? It's likely a really fascinating combination of both.
Section 5. Future therapeutic frontiers.
Notice the rapid metabolic response curve here. You might see normalizations like glucose leveling out in just minutes. But if you look at the longer timeline, actual tissue rejuvenation, like clearing out that toxic interstitial fluid and triggering deep cellular S-phase repair, that requires prolonged, consistent exposure over hours and days. Modifying that dense interstitial space via the vascular lymphatic loop takes serious time. Let's move to and see how this builds into real-world treatments. Notice the blunt systemic infusion at the top. These unprotected soluble factors are totally obsolete. They succumb to extreme dilution and fail to maintain the gradients needed to penetrate tissue. The true future architecture lies below. Loop-resilient therapeutics. Success means engineering treatments, like those targeted exosomes, that either artificially clear out interstitial toxins or utilize affinity-based targeting to survive the full vascular lymphatic loop totally intact. Which leaves us with this final, really provocative thought to ponder. By successfully engineering around the body's natural dilution barriers, how will these newly designed loop-resilient therapeutics completely revolutionize the future of human longevity and aging? The biology is complex, for sure, but the potential is absolutely limitless. Thank you for joining me on this explainer. Stay curious and keep learning.